Welcome back, everybody. Today we are going to take a quick time travel trip to your childhood. Maybe not. I don't know, my childhood, which was when? Indeed. Last time I laughed that hard, I fell off my dinosaur Huggins. All right, look. Oh yes, I'm gonna throw that one. It's gonna try it with every class today. All right, here we go. How many of you guys have ever played on a teeter-totter? Okay, can you give me another name for a teeter-totter? A seesaw. Okay, somebody who maybe didn't spend a ton of time in the U.S. as a child still might not know this. Anybody know what it's called in the Philippines? Because I have no idea. It's still called a teeter-totter? A seesaw still? Okay, so if I were to build a seesaw, is there one on this island? I mean, I got wood at my house and we make little ones in the backyard, but I don't. Okay, none of the parks though. I wonder why. I remember hating them because I was self-conscious as a child because I was kind of a heavy kid and never didn't like seesaws. All right. However, check it out. Let's think about a seesaw here real quick. Hypothetically, I have a seesaw running across. I'm going to go back to the other color. I have a seesaw. Now, it's just a big piece of wood, right? If I want this to become a seesaw, what do I need to add? There's an F word that's not factor or fraction or profanity. Not an empty crumb, but a full crumb. Okay, so the pivot, right? That's all we need. Check it out. We have a lovely pivot. I'm going to try my best to make this right in the middle. Yeah, pretty clever, right? Cool. Here's our fulcrum that we're dealing with. Now, when we deal with this, do you guys agree that if somebody heavy sits right here on this left side, the whole thing's going to make a revolution? This is our axis that we're looking at here because I can see that's just going to tip over that. So there's just rotational motion, which means when somebody sits here, as long as they have a mass, they apply some sort of force downward, right? Okay, are they some distance away from our axis of revolution? So we're applying a distance, or applying a force some distance away from something that's going to spin about, which means we have more than just force here. What do we have? Louder. We have torque is what we're after, or angular force, if you want to think about it like that. So hypothetically, let's say that we have two separate masses of the exact same size in everything, identical pieces. We have a mass sitting over here and a mass sitting over here. Now, my picture is not drawn to scale, but we can pretend that it is. Whatever the mass is, gravity pulls them straight down, right? Straight toward the middle of our planet, which means we get a force of gravity acting here, Fg, and we get a force of gravity acting here. Now, if both of these objects, children, whatever they are, doesn't matter, if they have identical mass and size, the gravity should act on them in the exact same way. At this point in time, if they're identical, will this thing spin? Probably not, right? Because we see that the torque generated by the person on the left is the same as the torque generated by the person on the right. So long as same force of gravity, what else would have to be the same? The distance. So let's just say that here's R1, we'll call it. And then this distance, let's call it R2. So we call them radii, remember, because if we're spinning, this thing's going to look like a circle. Now, if we have equal mass and equal distance, then we don't have any movement. If there's no change in movement, what do we say the net force acting on the system is? 0. Now, the only thing that we're going to change is instead of saying the net force, because we're talking very specifically about force creating rotational motion, we're not going to use the word force here. We're going to make the following statement. No change means, and we're actually going to write both of them. I'm going to say that F net, you guys just told me, was what? 0, which immediately implies that something else is 0. So the net force acting on these objects is 0, no change in speed. But when we shift this to a rotational system, like a seesaw, this implies something else is equal to 0. So not just the lever, it's not the lever, but it's the torque, right? we have no net torque acting on this thing. So we'll say, here it is, T net is also equal to 0. Now, I should include newtons here and newton meters here, but we have no net change. Now, another way to word this, nothing changes. In other words, what we could look at this as, or i.e., we could say that, hey, if this is object 1 and this is object 2, since we have R1 and R2, what we identify is if we were to take these, torque 1 plus torque 2, what should they add up to? 0. I'm good with that. We'll say newton meters. Or if we wanted to go a step further, I could subtract and say that they're equal but opposite. Now, the only other thing that gets weird about these problems, I don't really think that this is weird, honestly. I think that this is as nice of a problem as we can get. Hypothetically, the person on the left is heavier. They're going to fall down, which means the whole seesaw is going to rotate in a positive or negative direction. So that's a hard thing to think about. If I have this person heavier, the whole system would spin like this, right? Okay, and if this person's heavier, the whole system would have to spin like this, the opposite way. Okay, which of those is positive? So I heard top and bottom. Why bottom, out of curiosity? So you want to say right is positive? Now, check this out, though, because if I had just done this, does that change your answer? Because they're still going the same direction. I just moved where the arrows are. Now it looks like this one is going to the right, and this would be the positive. Do you see the issue? Okay, so in math, which direction is positive? If we stick out our right hand to be at 0 degrees, and we're making a 0-degree angle, which way do I spin to be a positive angle? Upward or counterclockwise. When we're looking at it, if this is the movement that we got, this is counterclockwise. This is the torque is greater than 0. Down here, or up here rather, I would be spinning in a clockwise direction, which means instead of being a positive torque, we would get negative torque. Just like we have positive angles that go counterclockwise and negative angles that go clockwise, same idea applies here. Okay, the only last little thing that we didn't look at in here is if we wanted to expand this. I know that the force acting on either of these is gravity. I can deal with that. Fg times what? That's the force. How do we get torque? F times R sine theta. Now, I'm going to write R1, I suppose, and sine of, and here's the big $1 million question. If you are applying a force here, what angle does this make? 90 degrees, and we're golden with it. 90 degrees. Now, trig review coming forward, because not everybody in here takes pre-calc, which is all of this trig stuff lately. I want you guys to point with your hand, with your right hand, start at 0. So on your perspective, it's over here. And then show me your rotation in 90 degrees. We go straight up. If I asked on the unit circle with a radius of 1, what is the ordered pair all the way up here? So I heard 0, 1, and I heard 1, 0. Here's a circle whose radius is 1. I want to know this point. 0, 1, which means when I see sine 90 showing up, what does it wind up becoming? 1, which works out super nicely. We see that they are indeed equal. Okay, the trig stuff. If you did not carefully watch the videos and things, I would strongly encourage it. We kind of blasted through trig kind of fast in the videos here because everybody that was in class was a chapter deep into trig with my pre-calc class as well. We still hit it, but if you have no idea what a radian is, come talk to me. Let's work it out. Cool. Seem okay? I guess we'll find out. So what I want us to do is we're going to do one more problem together, I think. But I want you guys to try first. This problem seems pretty, like this is as stereotypical as a physics problem as you're ever going to find. Huggins, I'm sorry, you had a question a second ago.
The 90 degrees, is that because it's perpendicular? Like, or not, like to the, I don't know.
Yes, so if we look at this picture, if we had pushed perpendicularly, and don't change your picture on your page, okay? If I'd pushed right here instead, notice that my theta winds up being this angle, which is the radius is exactly the lever arm, is what winds up happening. Cool. Good question. All right. So what I want you guys to do is, for this first problem, this is number 3 on your worksheet. I'm going to give you a moment, talk with your neighbors. I want to be able to eavesdrop, not eavesdrop. What's it called when you eavesdrop with your eyes? Watch. I want to be able to observe that you have the following stuff. I want you guys to take a second, get me my know, get me my find, and then get me an equation. I want you guys to talk it out. I want to hear vocalizations of your cognitive abilities with one another. Cool. I'll give you a moment. The mass of object B is 0.23 kilograms. How would you like me to write that down? Love it. M sub B. We'll use a subscript here. Equals 0.23 kilograms. I am too bold. I hate it. Okay. Beyond that, something else that I know. Number Bea. So the radius of A, I'm going to leave it just a little gap. Radius of A is, here we have to be really, really careful. Check for me your units of torque. What's the unit that we put on torque? Newton meters. What do we have R in right now? Centimeters. If I didn't hear you, Bea, that's my bad. Could we write 4.5 centimeters as meters instead? Move the decimal how many spots, which direction? 2 spots is what it'll take, but which direction? Left. Okay, so when we go to write the radius, I don't need to see the conversion. I'm going to take 0.4.5. I'm going to make it 0.045 meters. Okay, with that done, I imagine this next one's going to be the same. What is the radius of B in meters instead? 0.011 meters. Okay, I have another known that I saw, Fern, you had found. What's the other known that you included? You included a couple more. The acceleration due to gravity is, what is it on our planet again? 9.8. What is it on Mercury? I don't remember either, so I'm not going to hold you to it. 9.8. I do remember 9.8. I did Earth. Meters per second squared. Cool. My Zoom, one more thing. Theta, I heard somebody whisper. Now, we talked about it yesterday, but if we have a gear, whether it's a chain or not, if I look at the radius that we're dealing with, any chain is always going to be tangent to my circle, which means it touches at exactly one point. And from geometry, a tangent line on a circle drawn to a radius is always what angle? 90 degrees. So theta A and theta B in this situation winds up being 90 degrees. Cool. That is all of our known stuff. We've got it. What am I trying to find in this particular problem? Number, Tully. Mass what? Perfect. The mass of basket A, or object within A, whatever it winds up being. Okay, we have a ton of stuff identified at this point in time. Now, for this, they're hanging around this. So we have 2 pulleys that are connected together. Are we told that they're moving at all? Definitely not. And I'll just tell you, we're going to work with this assumption, and it's a safe assumption. Are they moving then, if they don't tell us they are? No. Why do I care about that? Why would that matter to me? Say that again? They balance out. Now, there's 2 different ways that we could write this down. We could start by saying the net torque is equal to what? 0. Or we could say, hey, to get net torque, you just take torque of A plus torque of B, and that's equal to 0. Now, one of them has to be negative, right? They're inevitably going to be. So what I would suggest we do is, instead of writing with net torque starting at 0, which is totally valid, I think it's going to be easier if you say torque of A is exactly equal but opposite to the torque of B. And we'll deal with the signs right now. One of these objects is going to cause stuff to turn positive direction, or wants to turn positive. The other one wants to turn it negative. Add to your desks, determine which one, and I'm going to ask you to justify. Talk with your neighbors. Is A or B producing a positive torque? I'll give you a moment. It should take pretty quick. Talk it out, though. I want to hear your ideas. Yep. So check it out. They both want to go downward. Don't use up and down for this. Do you agree with the arrows that I put up here to show that if A were to win, it would turn that way? Which, is that clockwise or counterclockwise? A would spin it like this, right? Counterclockwise. Which one? Because I heard both answers from you too. Okay, I might not have heard. Okay, so this is a positive torque, and this is my negative. Cool. With that in mind, since we're finding the torque of A, I'm going to sneak that there. Cool, because they have to be equal but opposite. Now, as we're dealing with this, do we have information about these things? We'll get there. How do you find torque? We have F, and for the torque on the left, it'd be F sub A, right? The force on A, due to gravity, but it's the force of A. And then I'm going to write this one time, R sine of theta, and that's equal to the force of B, and this should be RA as well, sorry about that, times the radius of B times the sine of theta. Moving forward, there is a 0% chance that I'm going to include sine theta anymore. How come? They're 1. So if we simplify this, because they're both acting at 90 degrees, sine of 90 is 1, we obtain FARA equals FBRB. Now, there's still a little bit left to do with this problem, because do I ever tell you the force that these things are acting, or that they're producing? Not at all. Is there information to find it, though? Holy gravity, Newton hooks it up. Force is equal to what times what? Love it, it's mass times acceleration, which means this would be ma, that's a mass of A, times gravity, g, times Ra, equals the mass of B, again times gravity, times Rb. I want you guys, from this literal equation with nothing plugged into it, I want you to solve this for whatever it is we're looking for. Once you have it solved, plug in your numbers. Before we come into the calculator, I want to highlight something. If we try to write g on both sides, and you can, but it's going to make your calculation much more muddled. What could I divide both sides by right off the bat? So the m's are different, but g would work, and then am I ever going to need to use 9.8 in my calculation ever? No, they're both going to divide out. This is the value in solving these literal equations. Solve this for MA, and we'll come back together once we have numerical solutions. I have an answer that we can check. Cool.
The sine of 90 is 1.
Sine of 90 degrees is 1. That is correct. Once we get down here, it is a great idea to think, were you guys expecting snow?
No.
How long has it been snowing?
I just realized.
Yeah, I just noticed it for the first time. Cool. All right, looking at this. If we're looking for a mass, we should have kilograms in the end, right? So check it. Just thinking this out, and this is a huge benefit, especially moving forward. What is this unit going to be? Kilograms. What are these going to be? Meters. We changed them, right? Meters over meters, what happens with those units? They gone, which means the only thing we're left with is kilograms. When we're looking for mass, that seems reasonable. We are on the right track. At this point is where I would finally pull the trigger to actually plug in the numbers. The mass of B, and I saw several answers give me the right thing here, 0.23 kilograms. times 0.011. And all of this gets divided by that lovely 0.045. And when all these calculations are said and done, we get the mass of basket A is equal to what? 0.056. If this is what you give me, Abigail, what didn't I like about this answer? Gosh, we need them kilograms. Cool. Now, as we go through these, the math here looks complex. Like when second hour walks in, if they see this, they're going to think, oh my gosh, what? I don't think we've done anything mathematically here with the exception of the sign stuff that's above like an Algebra 1. They're hard Algebra 1 problems, but every person in here has a capability and the intelligence, the math wherewithal to do these problems. I guarantee it. Cool. Super hard, super easy. Give me a scale of 1 to 5. 5 says I'm perfect. I could do these in my sleep. 0 says what the heck's a torque? Anywhere in between. Okay, cool. So what I want you guys to do is to have a little bit of creative freedom, and I want you to have creative freedom with number 4. Now, I will always include pictures for you guys, especially when they're complex like this. As a kind of hook it up for you guys, I will let you know that I have 5 knowns here. And what I would suggest, just so we can all talk about it at the same way, is let's pick out some of these knowns together before we start on the problem, just so all of our subscripts match. Okay. We have a cyclist with 65 kilograms of mass. They're standing on a crank on a bicycle pedal that's connected to a gear, and they have a 45-degree angle formed there. The crank is attached to a chain wheel, and it has a radius of 9.7 centimeters. We're trying to figure out how much force from the chain, which incidentally comes from us pushing on the pedal, right? The chain doesn't make it. But how much force do we need to stop the wheel from turning or to prevent it from turning? Now, as we look at these, I have a few subscripts that I would like us to use here. Anything that we know, any masses? The bicyclist has a mass of 65 kilograms. I indicate this with the mass of the bicyclist. Now, alternatively, P would also make sense for pedal, because it's the person acting on a pedal, but I'm okay with this. Okay, I want to commit. I'm not going to, I guess we already said it was 65. And there's one more thing that we have to deal with. Now, we don't have any other masses given in this problem, I don't think. But what else do we have? There's torque being generated by the cyclist stepping on the pedal. Cool. So I know that there's going to be a torque of the pedal in the end. What else is acting on this, though? Gravity's certainly there. We're trying to find what force, not the cyclist must put on this, but the what? The chain, because we assume that there's a person pushing down on this and it's just not moving, so the chain must be preventing that. So I'm just going to say that, hey, the radius where the chain acts, RC is what I will call that. What's the radius of the chain? 9.7 centimeters. Let's change that. 0.097 meters. Cool. Using B for bicyclist on the pedal and C for chain, I want you guys to knock out this problem. I want you to talk it out. I will not be speaking up at the board again until we have solutions. Cool. Give it a go. If we have stuff that's not moving, and sorry, I should have been recording that. We're looking for the force of the chain. If this isn't moving, then torque C pulling in the positive direction, the torque acting on the chain, had better be equal but opposite to what? Torque that the bicyclist acts on the pedal, right? Okay, looking at that, this is just another way to rewrite that my net torque is equal to what? 0. Now, Kalisha, you wrote something different, and all you did was just, don't erase it. You've written something different first, but notice what's going to happen. Could find the torque of C, it's the force that acts on C, times what? The radius of C times the sine of which angle? What angle is our bicyclist forming with the center of revolution, or the axis of revolution? 45 degrees. Or theta c, if you would rather do it that way. Theta sub c. Ooh, but careful, I'm backward here. I haven't put in any numbers yet, so I'm okay with that. This is c on the left. I don't know why I did c on the left. That's okay. Force B is just RB times sine of theta b. Now, I didn't write down theta b. Yeah, I did. It's right here. I didn't write down theta c. But we have a chain acting on a gear. What is theta c? It's 180? Why 180? If I have this radius and this force, what's that angle they form? 90. I like 90 a bit more. I'm going to include it here. I didn't include it on mine because I just let it fall out right off the bat. But it's true that it's 90. It's a chain. Okay. Once we're here, we're close. I know that this piece is going to disappear because sine of 90 winds up being 1. It's just gone. I'm just going to let it fall out. And we're trying to find for FC, right? Well, if I wanted to solve for FC, what would I divide both sides by? RC, anything else? If I look at just the left side, if I do this, RC, they're gone. And I also need this, right? The sine of theta C. Now, this is gone, and this is gone. And what's the only thing that remains on the left side? F of C, or F sub, sorry. And what are we solving for? Hey, look, that's convenient. Cool, so I'll divide this side by the same thing, RC times the sine of theta C. And once we get to here, it is essentially plug and chug, with one little caveat. Do we know the force that B exerts? Because what is, I said sine of B, didn't I? Which one should I have canceled out? When did you notice it? Was it just now or was it a couple minutes ago when I made that comment? What should you do in the future there, Angel? Sean, good catch. Angel, good catch. Speak up though. Okay, that one's 0, right, Sean? That's my bad. That makes this problem even easier. Now to solve for FC, what should we do? I'm going to divide by the radius of C. Now, as we look at this, I'm going to hold off on doing the top for just a second. The force of B, we do not know. Not exactly. Do we have enough information to find it, though? How do you find the force of a bicyclist on a pedal? You take their mass, M, B specifically, and you multiply it by what? G, and this is still times the sine of theta sub B. At this point, every single thing that's written on the right side of this equation is known to us. We will start tomorrow with this solution, and then we're going to expand on a little bit. I will give you the remaining 2 minutes to plug and chug. If you have a number, let me know. I'm happy to come check it. Man, I feel like I should give you homework tonight, but I don't know that I'm going to. Am I going to? We're not going to have homework tonight as long as you finish this problem. I will check this at the start of class tomorrow. Cool. 100 seconds left. You got it.